For now, it's time to take a deep dive in another nice case and to learn from a company that's really into tech. And we didn't ask anyone of this company because the title, in his job title, the official job title, he's evangelist, right? Evangelist on AI and machine learning, technical at Amazon Web Services. And we're going to get him on stage and give him the time to talk to us and to learn from him. He's going to get the first round of applause of the day. It's always a tough one. We need to get warmed up. I see someone warming up their hands. Yes, warm up the hands. Because you know what you will give, you will get back. So if you give a nice energy in the applause, we're sure to have a great story presented to us by the senior technical evangelist from Amazon Web Services, Shashank Prasanna.
That was a nice trick. I should borrow that. I'm Shashank, and I've been told most of you are from academia, so I'm an electrical engineer by training. My research background was in control systems and large-scale time series analysis. These days, I work for Amazon, and part of my job is to actually help scientists, developers, and researchers scale their machine learning workloads on Amazon Web Services, or AWS for short, which not so coincidentally is also the topic for my presentation today. And let's just dive deep quickly. And I want to start off with a high-level overview of a typical machine learning workflow. And a quick show of hands, how many of you do machine learning or involved with some machine learning research? Or wow, that's nice to see. That's probably around 70% of the room. Soon it'll be 100%. But at a very high level, and what I show here may or may not directly resonate with your workflow, but you'll hopefully relate to it from a conceptual point of view. So machine learning is a data-driven field, right? So you have to start with data, and the first step, of course, is acquisition of data and labeling data if you're doing supervised learning. If you're doing unsupervised learning, you're just acquiring data. And then there's the whole data preparation part in preparation for machine learning. And in a lot of organizations, these two steps are typically performed by separate data teams when they're dealing with petabyte scale data. But smaller companies, research organizations, research teams tend to do everything themselves. After that is when you design and run experiments. And the whole point of running experiments is to find sort of what works, what doesn't work, what is the best approach. And then once you've figured out what works, what doesn't work, you then do model development with the focus of deployment. We then optimize these models, prepare them for deployment, and finally go host them. And this becomes a full circle because once the model is in deployment, you want to look at things like drift detection, if the data distribution in the real world still matches the data distribution which was used to train the model, and if there's you can perform statistical tests or machine learning-based tests to see if there's if they are diverging, and then you want to retrain and update. So this is a full machine learning circle. And I want to focus on the blue boxes here today, primarily designing and running experiments at scale. And so why do we run machine learning experiments? Really for the same reason why you run experiments for any other scientific field. And the scientific method gives us with a systematic framework that lets you design and run experiments so you can make objective statements about some hypothesis that you've proposed. So in a machine learning example, this may look something like this. Say you're a banking company and you want to detect fraud, and you have data, fraudulent data from all over the world. Maybe you pose a question saying, should I deploy a single model for globally, or should I deploy separate models in each region? And you may hypothesize saying that maybe I want to deploy separate models because a global model may underfit, may not capture all the local dynamics in the incoming data to detect fraud. And then you want to run experiments. And experiment in the scientific method construct is an experimental procedure to determine whether you agree with the hypothesis or you reject the hypothesis. and then you interpret the results, and finally, if you reject the hypothesis, you ask a new question, frame a new hypothesis, and keep going through this process. Now, how is this different in a machine learning context? Typically, a machine learning researcher may want to do many of these things. First, they want to identify factors that affect model performance. And some of you who do this may call this hyperparameter search or hyperparameter optimizations. But there are also other reasons why you want to run experiments. One is you want to explain the root cause of accuracy, much like what you would do in a design of experiment sense. Also, you want to compare different approaches. You've chosen two or three different approaches, and you want to see if one is better than the other, and you can design an experiment around that. Also study variability and robustness. How you can do sensitivity analysis and see if the model does or does not perform as expected when you have variability as you would expect in real world scenarios. And also if you want to find sort of a Pareto optimal solution for competing objectives. So accuracy is, of course, very important to all of us, but you may have model complexity, which kind of adds to the runtime, and you may have competing objectives, so you want to find sort of the best balance between these. So a few different reasons, I'm sure many other reasons why you want to run experiments. And if you look at the standard sort of design of experiments model, machine learning system is no different from any other system. You have a bunch of factors that you control, and these include things like what algorithms, what optimizers, what hyperparameters, and many other things that are under your control. And there are a lot of uncontrolled factors, and this could be bias in data, could be earthquake that's happening where you're running the experiment, so stuff that's not under your control. And then you have responses, which could be not just accuracy, like generalization accuracy, but as I mentioned, variability, reproducibility. In production, you want, say, 50 millisecond latency when you invoke the model and stuff like that. So there are other criteria that becomes important as you use this in production. Okay, so everything I spoke up till now was sort of the importance of experimentation. I think the community, there's a lot of research happening there. There have been some recent papers on how the importance of interpretability in machine learning. I hope we see more of this being used in industry as well. And one field in the scientific community which actually does this very well is in high energy physics. They use machine learning models to detect subatomic particles, but they do it in a very systematic way, putting a nice framework around how they experiment. So sort of slowly shifting focus to the scaling aspect of this talk. So when you run experiments, when you do machine learning, you're typically looking for three key ingredients. The first is, of course, your frameworks and your code that you write. And then you want access to compute, like CPUs and GPUs. And you also want storage, because this is a data-driven field. You want to store tons and tons of data. And for many of you, the setup may look something like this. You have your laptop. Maybe you have a workstation with a couple of GPUs. And if you're really lucky, you may have additional workstations or a local cluster to use, perhaps a supercomputing cluster in the university. And for the rest of you who started to do this in the cloud, you may quickly get access to a beefy GPU-based instance in the cloud, and you have your data sets in the cloud as well, so you're able to run experiments. Now, it used to be that many, many years ago, in fact, even when I was doing some of this work, you would actually run experiments on a computer. You could easily track them with a spreadsheet or using Vim, because who really uses Emacs? That was a joke. I have one very good friend who uses Emacs. But you would run this in a loop, and then this was OK. This worked fine for a lot of use cases. But with more data now and more computationally expensive approaches like deep neural networks, this starts to get a little difficult running this on a sort of a setting that we have today. And it turns out that most of the experiments that we run are embarrassingly parallel, like searching for hyperparameters and others. So from what you have on the left, you can actually move to a framework that looks something on the right, where you actually scale this out. So instead of having this run sequentially, you can run this on parallel in a cluster. Sounds pretty simple and straightforward, right? But turns out there are many, many challenges in doing this. And conceptually, it makes sense. Oh, let me just run these in parallel. But a lot of things don't translate well when you start to move things to the cloud or a large-scale cluster or supercomputing cluster. For one, managing software is a real pain. If you ever moved from a development environment in Windows and moved to a cluster that runs a different operating system and different libraries and different versions, it's painful. And managing cluster is something I and you don't want to do because we're not IT or ops people, right? And infrastructure management, provisioning hardware, again, not something we want to do. And the elephant in the room is a cost. Now, if I were to run, if it cost me X dollars to run something in a loop on a single system, and if I run this in parallel, would the cost be the same, more or less? We want it to be the same or less, right? You want to pay for what you use, but you don't necessarily want to upfront pay for excess compute like this. And these are genuine challenges people encounter. So I want to dig deep into each of these 4 boxes. The very first box is software management. And a machine learning stack is incredibly complex. And you may have said this, or you may have had colleagues or others who say things like this. You have code that requires to be built, several dependencies. Your code sometimes is not taking advantages of your hardware resources that's available on your computer. And you may not have the right GPU libraries. If you don't know what those libraries are, I don't blame you because the stack is complex. It's running slow. You're not sure if you compiled it with the right instruction set. You just updated your drivers and everything just breaks, right? And this is a very common challenge which I used to face a lot, which is you run something on one version and then you move it to another cluster and then you have a different version of operating system. All of these challenges makes portability and scaling really, really hard. So what ideally should be like this, wherein you have your code in the pink box on a development cluster, you seamlessly move it to a training cluster, and then everything magically works, right? But in reality, it's not one pink box, but it's a multicolored box of dependencies. And there will be changes all the way from your operating systems to the kernel, to the drivers, to the CPU libraries, to the GPU libraries, the framework dependencies, and the framework API itself. The whole list of dependencies, and this introduces multiple points of failure. A quick side story, when I was still doing research in grad school, we were analyzing time series that took me 2 hours to work on a single time series. So I would scale this on a university cluster. And my development environment was on a Windows box. I used MATLAB, Fortran, and C. If you know what MATLAB is, I'm sure you're over the age of 30. And migrating this code to the cluster was actually quite painful. I had to recompile all the different libraries for the cluster. And if they updated something, I had to do this all over again. And there was no other way. I mean, the only way to do that was to actually make sure that I go through this whole process again. Thankfully, there's another community which has come up, has made a lot of progress, and for a completely different domain, but now being used for machine learning as well, which is sort of the container community, where you can use tooling to actually build packages, lightweight packages of your entire software stack, not just your code, but also your configuration and dependencies. So it makes this deployment very, very portable. Typically, this was being used for deployments, like deploying a microservice on the cloud. But you're seeing a lot of container use now for machine learning training and also in high-performance computing. And it's because it solves this big problem of dependencies. The core technologies have been around for a while, but it's gotten popular only since 2013 or 2014 when Docker made this popular, which wasn't there when I was back in school. And your now deployment or training sort of paradigm changes to you develop your code on the left, you package it up into a container, and then you push it to a registry, which is sort of an app store. And then on your training cluster, or could be a collie, you could just pull it, and everything automatically works in most cases. Most of the dependencies are encapsulated there, except few dependencies that are outside the container, and those are still some points of failure, but largely solves the problem with machine learning because the community is moving so fast. If you ever use TensorFlow and a 0.1 version release just breaks all your previous code. And this way you can make sure that you have consistency and reproducibility. So you can solve the software management challenge with container technologies, but you still have challenges with cluster management and infrastructure management. And here's sort of the lay of the land with what's available in this that addresses these challenges. You have compute at the bottom, which is where you run your software. These are your traditional instances with CPUs and GPUs. This is your sort of the infrastructure hardware layer. Now, you want something to be able to run jobs on this compute. Think of the management layer as your operating system, and the compute layer as your computer itself. But the management layer here is an operating system for a cluster. So all the things that you don't think of when you run an app on your computer, like what CPU threads are you using, how much memory are you using, all of that is abstracted away from you. In the same way, cluster management tools like Kubernetes and ECS, they abstract away where something runs. You just have to ask it to do something, and it'll go find the right resources. It's sort of like an operating system for a cluster. And then you want to have your app store or your registry where you actually store your software. Now, this is a pretty common setup in most companies where they run compute at scale. And everything I've shown here has nothing to do with machine learning specifically. This is a sort of a general framework. And for machine learning specifically, there are a few other abstraction layers. There are high-level layers, managed services like SageMaker, available on Amazon. In the open source community, there are things like Kubeflow project, came out of Google and contributed to the open source community. So these projects actually add an extra layer of abstraction, so you can focus on machine learning and not actually managing and running clusters. Through the rest of this talk, I'll focus on these two layers here. One is SageMaker, which is fully managed, where you absolutely don't have to manage cluster. And with Kubernetes, where you have to manage a cluster, but provides you some abstraction. Quick show of hands, how many of you are familiar with either of these two services? Okay, fewer than I expected. But this is sort of the process, mind shift, right? As if you're doing machine learning, eventually you want to scale. You have to, whether you like it or not, sort of have to pick up some aspects of scaling. And you'll particularly be interested in SageMaker, which helps you really abstract away all the nitty-gritties of managing infrastructure. So one of the main reasons why researchers and data scientists run experiments is to actually find the right hyperparameters. This is probably the key reason why you run large-scale experiments. And for those of you not familiar with this topic, these are options that you set well ahead of time before you run training on your data sets. And these are things like learning rate and batch size and what kind of optimizer you want to use and stuff like that. These are not optimized as part of the machine learning process, but setting these to the wrong values has a detrimental effect on the actual accuracy. And it widely varies how your model performs. And there are many strategies to find the best ones. There's more naive ones like random search and grid search. There's a little more smarter techniques like Bayesian optimizations, and there are new evolutionary optimization techniques using genetic algorithms and others. And think of these as sort of tuning knobs that are pilot sets before putting the flight on autopilot, right? These are options that the pilot sets because the pilot really knows what to set. But finding the right ones means going through becoming a pilot. In this case, searching through all the combinations to find the right option. So with that, I want to quickly show you sort of a demo of how to scale these workloads. In this case, I have a typical machine learning training script, and I want to be able to run a combination of hyperparameters at scale. And I want to do this in parallel because they don't have any sequential dependencies on each other. They're all separate processes that I can run separately and sort of take a look at the results. And from a workflow standpoint, this is what it looks like. So you start with your training script, you develop it locally just as you do today. And then you have your Python script I mentioned, could be any arbitrary language or code. You put this in a container so that you now have this reproducible environment. And if you're using the higher level service like SageMaker, it'll automatically, you just specify that you want to run 16 experiments in a cluster. It'll automatically provision the cluster for you, go run these 16 experiments, shut down the cluster for you, so you only pay for just the duration of execution. If you were running these experiments on the cloud anyway, on an instance that you use on the cloud, you would be paying for the same amount because you're sort of running this in parallel, but you're still paying for each instance versus doing it sequentially, you're doing it parallel. So let's quickly dive into sort of the results of this analysis, and I'll quickly go over what this looks like from the console. I have an experiment that I finished running just earlier today, and I'll show you quickly sort of the results. And what you see on the screen is me setting a couple of hyperparameters here. These are my epochs and learning rate and batch size and others I mentioned. And if I want to just run a single experiment, all I have to do is specify where my training script is, which is this, and all the dependencies in a code folder. If you have any, the type of instance I want to run it on, in my case, it's a GPU instance. And I specify where my data set is, which is typically on the cloud, in my case, Amazon S3. And when I hit fit, it'll go and run this training for me. And at the very end of this training, you see it trained for 759 seconds, and that's what I'm paid for. And the instance was spun up for you and shut down for you, but that's just one experiment. Now, if I want to scale to 16 experiments, I just have to specify the hyperparameter tuner job here, and I just say max jobs are 16s, but run 8 of them in parallel. Notice I'm not doing any instance launching, and I'm not managing any of the infrastructure. All this is abstracted away for you. And I just specify how much I want, and it'll go run this for me. And back in my console, I can take a look at the hyperparameter tuning jobs. I just ran this one today, FTC 2019. And you'll see all my jobs were scheduled automatically for me. I can look at the objective values. So there are some that are 83% accurate, some are much lower. You obviously want to avoid that. I take a look at the best training job, and here's the hyperparameter combination that gave me accuracy of 83.9%. Now, is this the best model ever? No, because this, for many of us, this is where the journey starts. Okay, you have a good starting point. Now I can go iterate upon this and try to find something better, right? But the whole key point that I wanted to make is that you want to focus on this and not actually managing infrastructure. But you do want to scale, but you don't want to manage infrastructure. With that, what I showed you was using SageMaker, but there are other services that let you do something very similar. And Kubernetes is an open source project. It's a cluster management, orchestrator, and scheduling tooling. And it has additional packages like Kubeflow and also Katib, which is a hyperparameter tuner and a network architecture search sort of tooling on top of Kubernetes. And you can also use this in using services like this. Often, you have to manage your own cluster. It's still a lot simpler than what it used to be back in the day. For example, with a single line of code, you can set up a cluster. You just run create cluster and specify how many nodes and GPUs you want, and boom, you have a cluster 15 minutes later. And now you have a cluster warm and running. You can submit jobs. You can do large-scale search, distributed training, and all that. The only difference here compared to my previous approach is that you're provisioning the cluster well ahead of time. which means the cluster is warm and running all the time. If you're not using it, you're still paying for it, right? Versus when you use a fully managed service like SageMaker, you actually just pay for the duration that experiments ran. But for a lot of you, this may be the better option, especially if you have your own, especially if you're standardized on Kubernetes for whatever reason. And I know many organizations do this. They just standardize on something and just want to use that. And setting up additional tooling like Kubeflow, I don't intend to read this, but my objective here was that setting up other packages on top of it is not really straightforward. You want to have some ops expertise, especially if things go wrong. If things go right, great. If things go wrong, often I have no clue how to debug these things. I have to go find someone who has IT ops expertise to actually debug these things. So to sort of quickly recap the couple of options we saw, you can scale up instances on the cloud with CPUs and GPUs and manage them yourselves. If you want to run experiments at scale, you can spin up multiple of these instances, but you're in charge for making sure that they're running, they're healthy, and if you want to start using them cohesively as a cluster, it's completely on you to manage them, and you have to rely on IT or ops expertise. And this can be cost effective if you know what you're doing. So if you set up sort of the right auto scaling and stuff like, if you know what you're doing, this can be very cost effective. But for a lot of us, we don't want to manage things at that level. The management layer with ECS, which I didn't talk about, is another service, but Kubernetes, which is very popular open source approach, is to set up a cluster manager. And in many cases, it's difficult to get started, but once you have a cluster set up, it's super easy to scale. You just tell it, I want to run things on 16 nodes or 32 nodes, and automatically scale the job for you. You still have a lot of management that you have to do yourself. It has better support for machine learning use cases, especially with Kubeflow. The project is still relatively new. It's a community-driven project. There are a lot of new capabilities coming in every day, and especially packages like Catib that'll do network architecture search, which you may know as AutoML, where it'll automatically find the networks for you. And here, again, cost optimizing is sort of on you because you're managing the cluster upfront, and you can set up rules so that you shrink the cluster when you're not using it. And if you want to sort of fully managed sort of a solution, with SageMaker, which is a managed service, you just, with a couple of lines of code, what I showed you, just specify how much resources you need, and it'll automatically scale your experiments on the cloud. And there are many APIs there that are designed for machine learning workloads. And if you're using some of the built-in algorithms, you don't even have to deal with containers. You just run your experiments. Ultimately, what works for you is whatever works for you. If you want to manage your instances, that's the best way to do it. If you, small teams that don't have IT ops experience, just want bursts of activity on a large cluster, you don't have access to a university supercomputing cluster. I was fortunate to have that until I ran out of credits on our cluster. But if you do want to, this is a very cost-effective option because you just scale out and then you just shut down everything. It automatically shuts down everything once you're done. And sort of bring everything back together, I sort of spoke about two completely distinctive things today. First is the importance of experimentation in machine learning. And I think it's important that as academics and researchers and also organizations, we start thinking about machine learning approaches as a scientific field and not just an experimental area where you want to be more thoughtful about how you conduct experiments. And for a lot of us who are not in the infrastructure space and the HPC space, we have to start embracing some of these other technologies like container technologies, because this is what makes your life easier as you scale. It's easy to do things on a single instance, which is called scaling up. You just add more compute to the same instance. But at some point, you want to be able to scale. And although many services like this make your life easy, you still want to embrace some technologies like containers and leverage services like SageMaker and Kubernetes that let you manage the experiments on a cluster. And with respect to cost, you can decide if you want to be able to manage your own cluster because you're good at managing costs on your cluster, or you want to use something fully managed like Amazon SageMaker, where you just pay for what you use, right? Everything I mentioned is mentioned in documentations. There are examples on GitHub. I believe I also pushed the code that I just showed you to my GitHub account. I can share the link afterwards. There are plenty of blocks. The thing I like about AWS where I work is this is the intersection of two things I like. One is machine learning, and the other is scalable computing, high performance computing. And increasingly we are seeing organizations and researchers doing things at scale, and this is an exciting, very exciting field for me. And we have tons of resources on blocks if you want to try them out yourself. And again, I'm more than happy to answer questions either today, or if you have questions tomorrow, next week, next month even, just feel free to reach out to me. It's what I do. It's part of my job. I just enjoy bridging the two worlds and helping you sort of run things at scale and be more productive. With that, I want to thank FTC team for giving me this opportunity, and thank you for listening.